All right, so the next chapter we're looking at is similar to acid-base chemistry, but instead of moving protons around, we're actually going to be looking at moving electrons around. And this is called oxidation and reduction chemistry. We'll take a look at the historical context. Historically, people thought of oxidation one way. They thought of it very simply as reacts with or gains oxygen. Actually, I'll just write this all out. Makes sense, right? So if it's an oxidation, it should be reacting with oxygen. A good example of this would be leaving iron out in a wet environment. It'll eventually rust and form iron oxide, right? So it gained oxygen in that reaction. And then conversely, with reduction, you remove an oxygen. From an oxide. All right, which do you think is more common in our environment, oxidation or reduction? Oxidation, definitely. We're surrounded by a ton of oxygen in our atmosphere. If you remember back to the oxygen lab, it's about 20% in our atmosphere. It's pretty hard for biological organisms to survive, but we've evolved to be able to withstand that oxidative stress, and we've got biological mechanisms to handle it. All right, so oxidation and reduction historically always had to do with the gain or loss of oxygens. Let's take a look at the more modern definition. And oxidation is no longer about oxygen, unfortunately. Instead, it has to do with a loss of electrons. And reduction is the opposite. It has to do with the gain of electrons. There's a bunch of mnemonics you can use to remember this, but my favorite one is oil rig, where oxidation is loss. And then reduction is gain. There's also another one that some of you may have heard called Leo goes grr. You can also use that one. But I like oil rig. Oil rig's simple and to the point. Oxidation is loss, reduction is gain. Does that make sense? All right, so I'll show you some general features. And I know some of this will be review of what we've already discussed. But oxidation, we said, is loss of electrons. That's the best way to describe it. Reduction is gain of electrons. Oxidation often has a gain of oxygen, but not always. The best definition has to do with the movement of electrons. And reduction often has loss of oxygen, but not always. It depends. And then conversely, you can look at hydrogen too. With oxidation, there's often a loss of hydrogen. And for these, there's often a gain of hydrogen. However, like I said, this description describing the movement of electrons is the best way to describe oxidation or reduction because it applies 100% of the time. If you're looking at oxygen and hydrogen, it only applies some of the time. So it's not the greatest tool for looking at a redox reaction. All right, does that make sense? This is a big deal in biology, so if you are taking biology classes, you'll see a lot of these reactions occurring within cells. All right, so let's do some electron bookkeeping where we keep track of whether electrons are being gained or lost. And I'll give you some hints too. The first one is that elements by themselves have no charge. So we always treat them as neutral or a charge of 0. And then number 2 is I like to draw the scale where I've got oxidation going up. So I'll just write oxidation like this and reduction going down. And the way I remember this is by creating a scale over here where if you're going more positive, you're going up. That means you're getting oxidized, right? So oxidized means you're getting more positive. And then more negative means you're getting reduced. And then in between, you've got neutral. So for example, if you're going from neutral to more positive, you're going in the oxidative direction. If you're going from neutral to negative, you're going in the reduction direction. Does that make sense? It looks pretty strange right now, but let's see it in context and then we'll go back and look at this again. So I'll show you a few examples. So the first example I have is with iron. And we said that if you leave iron out in your yard, it can react with oxygen. And it can make a metal, make iron oxide. Let's name this metal too really quick. What would this metal be called using the full formal name? Fe is iron. Would be iron 2 or iron 3? Be iron 3 oxide. Okay, so when we react iron with oxygen, we get iron 3 oxide mostly. All right, now what we need to do before we begin is we need to bounce this equation. So let's try to bounce it really quick. I also forgot my third rule. Whoops. Sorry. Third rule, I'll squeeze it in the bottom here, is treat all other atoms as ionic. I'll try to make that look prettier later. All right, so who feels like they got this bounced already? Okay, so let's go ahead and bounce this. I'm going to erase this just to keep it clean. What prefix should we have in front of the iron? 4. What about the oxygen? 3. And for the iron?
2.
Or the iron oxide, excuse me. Yep, this looks like it's completely balanced. All right, so now let's take a look at what's going on here. If we think about iron, right? Iron in this case, because it's an individual element, we're going to treat this as neutral. And then what's the charge going to be for the iron over here, each individual iron atom? 3, exactly. So when we named it, we called it iron 3 oxide. That means each of these iron atoms must have a charge of 3+. So I'm just going to treat this as ionic, Fe3+, like that. All right, now when we go from neutral iron to iron 3+, are we gaining or losing electrons? Losing electrons, exactly. We're getting more positive. So we'd say each iron lost 3 electrons. All right, so if an iron atom was losing electrons, was iron being oxidized or reduced? Oxidized, right? Oxidation is loss for oil rig. So iron was oxidized. So I like to kind of pencil it out this way and then just circle or highlight my items being oxidized or reduced. All right, let's do the same thing with oxygen really quick. All right, with oxygen up here, it's by itself, so it must be neutral. And then what charge does oxygen have if we're treating it as ionic? It's in group 6A, -2. So it'll be O2 negative. So if we go ahead and do the same thing here, it looks like each oxygen gained 2 electrons. That means that oxygen was reduced. That's the key feature in these reactions, is they're often called redox reactions because one half of it is being oxidized, the other half of it is being reduced. Typically you have this bouncing of transference going on. Does that make sense? All right, I'm going to slide this down so we have more room. Let's do a few more practice ones. Sorry, I'll leave this up here. We'll do the one that we saw in lab, or actually, we'll do a different one. We'll do CuO. What would this be called? Copper oxide. We need a Roman numeral in there because copper is a transition metal. Copper 2 oxide. So copper 2 oxide plus zinc is going to form zinc oxide, and we know it must be zinc 2 oxide plus copper metal. All right, so just like before, we need to figure out which atoms were being oxidized and which were being reduced. So let's go ahead and start with the copper. So I'm going to start with the copper here. What charge does this copper have if it's ionic? It's not by itself. 2. So we'd say copper 2+. Over here, copper is an individual element, so we treat it as neutral. So if we're following this, we can say, all right, copper, did it gain or lose electrons here? Gained. So we'd say each copper gained 2 electrons. So copper was oxidized or reduced? Yeah, copper was reduced. All right, so we can highlight that. We can call that good. All right, now let's try the next one. We'll try oxygen here. Oxygen's not by itself, so we treat it as ionic. What would the charge be for oxygen? Yeah, it'd be negative what? 2. So 2 negative. We've got oxygen over here. We're treating it as ionic. What would the charge be? The same, exactly. So this would be oxygen 2 negative. Did oxygen gain or lose electrons? No. So there was no change. Meaning this wasn't oxidized or reduced. It's basically just hanging out in this reaction, so we can ignore it more or less. Does that make sense?
Why is the charge of oxygen?
Yeah, so if we look at oxygen as an atom, it's got 6 valence electrons. Like we said, atoms want to form a complete octet. And so what it will do is it'll steal 2 electrons from something else One of them will fill in this open spot right here. The other one will fill in this open spot right here. When we complete the octet, it has 2 extra electrons, so we treat it as 2 minus. So a simple thing you can do is look at the valence and then figure out how many more electrons you need to have a full octet. Yep. All right, so some atoms in these reactions don't really do anything. They're more just spectators, and that does confuse students, but it's always good to check. So I'm just going to erase this for right now. Let's now move to the zinc. What charge will this zinc have? Be neutral, right? So zinc will be neutral. And then over here, what charge must this zinc have? 2 plus. Oops. So did zinc gain or lose electrons here? Lost 2 electrons. So I'd say each zinc lost 2 electrons. That means zinc was oxidized or reduced? Oxidized. And we could go ahead and highlight this too. And it's also interesting too, because just like we saw with bouncing reactions, we also have to bounce electrons being transferred. So for example, with this reaction, we had a copper atom gain 2 electrons, where the zinc lost 2 electrons, so the net movement of electrons bounced out, right? That also has to be taken into account when you're bouncing reactions. We're going to do just really simple ones, but if you go on into general chemistry, it becomes a little bit more complicated. All right, let's try a few more. And this time I want you to work with your partner or neighbor to see if you can figure these out. Let's do magnesium plus chlorine gas to give us magnesium chloride. This time we can't cheat and look at oxygens being gained or lost because there aren't any. And then we'll do a second one. We'll do magnesium plus N2. That's our nitrogen gas to make magnesium nitride. So Mg3N2. And be sure you bounce everything too. So identify which element was getting oxidized or reduced. All right, let's try this really quick, just for the sake of time. What charge does the magnesium have? Neutral, in both of these. So I'm going to go ahead and write neutral and neutral. One thing I did forget to do is bounce my equations. The first one looks bounced, bottom one not quite. I need 3 in front of the magnesium to bounce that out. Now it's bounced. Okay, but in either situation, magnesium is neutral because it's by itself, right? All right, let's do the next ones. Up here we've got Cl2. It's still chlorine by itself, no other element types, so this would also be neutral. Same thing with nitrogen. It's by itself, so we'd say this is neutral. So we've identified that. It's pretty straightforward. Let's go over here. What charge does magnesium have when it's ionic? +2. We can tell that on the periodic table. So we'd say Mg2 plus. Did magnesium gain or lose electrons? Yeah, so each magnesium lost 2 electrons. So is it oxidized or reduced? Oxidized. So that's pretty straightforward. We can do that one. All right. Same thing is true for the reaction right above. We know we're going magnesium 2 plus. So in this upper reaction, each magnesium lost 2 electrons, meaning magnesium was oxidized. Like I said, you don't always want to rely on looking at oxygen because in these examples, magnesium was oxidized even without oxygen being present. All right, now let's do the next one. If we think about chlorine right here, what charge does chlorine have when it's ionic? -1. So we'd say Cl 1 minus. So it looks to me like each chlorine gained 1 electron. That means that chlorine was reduced. So I'll highlight this. And if we're counting the number of electrons going in each direction, we had 1 magnesium losing 2 electrons, but we had 2 chlorines, each of which were gaining 1 electron. So the net movement of electrons bounces out. All right, let's do the nitrogen on the one below. What charge does nitrogen normally have when it's ionic? -3. Okay, so we'd say N3 minus. So in this example, we'd say each nitrogen gained 3 electrons. That means that nitrogen was reduced. And just like before, we need to make sure that the number of electrons being transferred is the same in both directions. So we had 3 magnesiums, each losing 2 electrons. So that's a loss of 6 total electrons from all the magnesiums, right? And then if we look at the nitrogens, we had 2 nitrogens, each of which gained 3. So that's a net gain of 6. So 6 movements, or 6 electrons were moved around in this reaction. Does that make sense? All right, I think that's where we're going to stop it today. Like I said, if you can, take a look at your pod and try to identify which elements were gained or reduced, but it won't be due tomorrow because we haven't talked about oxidizing agents and reducing agents.